Close your eyes. Take a long, slow breath. Let your body sink a little deeper into the mattress beneath you. And let me take you somewhere extraordinary tonight, somewhere dark and ancient and impossibly beautiful. We're going to talk about black holes, those silent, patient mysteries at the edges of our understanding, those places where the universe folds in on itself and keeps its deepest secrets. There is nothing to fear in what I am about to tell you. These things are far away. They are ancient and quiet and magnificent, and learning about them in the soft dark of a room where you are safe and warm is one of the gentlest pleasures the universe has to offer. So breathe slowly, let your shoulders drop, and come with me. A black hole is a region of space where gravity has grown so powerful, so overwhelming, so absolute that nothing in the universe can escape it. Not a rocket, not a beam of light, not a whisper of radiation, not anything. The gravity at and beyond a certain boundary becomes, in a very literal sense, infinite in its pull. A one-way door in the fabric of space and time, beyond which everything flows inward and nothing flows out. It is perhaps the most dramatic thing the universe ever does. The act of pulling so hard on reality, the reality simply gives way. And yet, from a distance, a black hole is invisible. It emits no light of its own. It announces itself only through its effects, the way it bends and distorts the light of everything around it, the way it pulls gas and stars into graceful spiraling orbits, the way it warps the very shape of space in its neighborhood. It is darkness defined by the light it influences, silence defined by the sounds it swallows. And as you lie here, breathing slowly, letting the day release its grip on you, think about how remarkable it is that something so extreme, so absolute, so utterly beyond everyday experience, exists in the same universe as this quiet room, this comfortable bed, this soft and ordinary night. The boundary of a black hole, the point of no return, has a name that sounds almost poetic. It is called the event horizon. Beyond it, no event can ever send a signal back to the outside universe. Whatever happens past that line stays there, forever, sealed away from the rest of reality. And yet, the event horizon is not a wall. It is not a surface you could reach out and touch. If you were falling toward a black hole, you would not feel a bump or a jolt when you crossed it. There is no membrane, no physical barrier, no dramatic announcement. The event horizon is simply a mathematical boundary, a line in space-time where the geometry of the universe changes its nature entirely. On one side, the future is open. You can choose to go left or right or up or down. On the other side, inside the event horizon, all futures lead in the same direction, inward, toward the center, toward the singularity. The universe beyond the event horizon is a place where the concept of escape simply no longer exists. Not because something is stopping you, but because the geometry of space-time itself has removed all outward pointing paths. Every direction leads in. There is a strange quietness in that thought if you let it settle gently. Not menacing, just absolute. Like falling asleep. You don't fight it, you don't push against it. You simply go in the only direction that remains available to you. And then you are somewhere else entirely. Black holes are not, despite what the name might suggest, holes in space. Space does not have a gap in it where a black hole sits. The universe does not have a missing piece, an absence, a void punched through its fabric. A black hole is a thing, a real physical thing, made of matter so extraordinarily compressed that its gravitational field has become absolute. Think of it this way. Everything with mass has gravity. You have gravity. The Earth has gravity. The Sun has gravity. A black hole simply has so much mass packed into so small a space that its gravity dwarfs everything else in its neighborhood. The sun's gravity holds the Earth in its orbit. A black hole's gravity holds light itself, the fastest thing in the universe, in its grip. It is not an absence. It is a presence, an overwhelming, all-encompassing, profoundly patient presence. And at its very center, at the heart of all that compressed mass, is a point called the singularity, where, as far as our mathematics can tell us, density becomes infinite, where the equations of physics, which describe everything else in the universe so beautifully and precisely, simply stop working. The singularity is the place where our map of reality runs out, where the territory extends beyond what our instruments can describe. And there is something humbling about that, something that invites a kind of quiet reverence. The universe keeps some of its deepest secrets very, very well. And as you breathe slowly in the dark tonight, it is perhaps enough simply to know that those secrets are out there, patient and profound, waiting in the heart of the darkness between the stars. Every black hole carries its own story and the geometry of space-time around it, and that geometry is described with extraordinary precision by Albert Einstein's general theory of relativity. Published in 1915, Einstein described gravity not as a force, not as some invisible hand reaching across space and pulling things together, but as the curvature of space-time itself. Mass curves space, energy curves space, and everything moving through that curved space follows the curves, the way a ball rolling on a curved surface follows the contours of the surface. Near a black hole, the curvature of space-time is extreme, so extreme that all paths in every direction curve inward toward the center. There is no direction you could point that leads away. General relativity predicted the existence of such extreme curvature in principle, though Einstein himself was skeptical that nature would actually produce conditions extreme enough to create a real black hole. He thought the mathematics was pointing to something that would never truly occur. He was wrong. The universe, it turns out, is not shy about going to extremes. It produces black holes regularly. Whenever a sufficiently massive star reaches the end of its life, whenever neutron stars spiral together and merge, whenever the conditions are right for gravity to win its ultimate victory over every other force, general relativity, which Einstein developed through years of solitary, patient mathematical thought, turned out to describe these objects with breathtaking accuracy. His equations, over a century old now, are still the best tools we have for understanding the geometry of a black hole. Let that patient, extraordinary achievement carry you gently towards sleep. Albert Einstein, for all the revolutionary power of his theory, did not believe that black holes actually existed in nature. He accepted the mathematics. He understood that his equations permitted solutions corresponding to what we now call black holes. But he believed that some physical process would always intervene to prevent a real object from collapsing to that extreme. He thought that stars would always find some way to support themselves against complete collapse. Through rotation, through pressure, through some mechanism not yet understood. He spent years trying to prove that the singularities his equations predicted were mathematical artifacts, not physical realities. He was, in this particular conviction, wrong. But his skepticism was not unreasonable. It came from a deep instinct that the universe, in its elegance, would not permit infinite densities. That instinct has driven much of the theoretical work on black holes since his time. Physicists still wrestle with what really happens at the singularity, whether it is truly infinite, or whether quantum effects smooth it out into something finite and strange. In a sense, Einstein's discomfort with his own prediction has been one of the most productive forces in 20th century physics. It pushed theorists to go beyond general relativity to reach for quantum gravity, to try to understand what nature actually does at those impossible extremes. The man who gave us the theory of black holes never believed in them, and his disbelief pointed, indirectly, toward the next great theory still waiting to be written. Even in being wrong, Einstein was generative. That is perhaps the deepest kind of genius. The name black hole was coined in 1967 by the American physicist John Archibald Wheeler during a talk at a conference in New York. Wheeler was one of the great physicists of the 20th century, a man who had worked on the Manhattan Project, who had collaborated with both Einstein and Bohr, and who had spent decades thinking about the most extreme implications of general relativity. Before his coinage, these objects were called by various unwieldy names. Gravitationally completely collapsed objects was one common term, which you can understand why did not catch on at cocktail parties. Wheeler needed something shorter, more evocative, more true to the nature of the thing. He settled on black hole, and the phrase, vivid and immediate and just slightly ominous, spread through the scientific community and then through the wider world with remarkable speed. Within a few years, it was everywhere. Wheeler had an extraordinary gift for language. He also coined the terms wormhole, quantum foam, and the famous phrase, it from bit, the idea that physical reality is at its deepest level, informational in nature. He understood that naming things matters, that the right word can open a concept to the imagination in ways that equations alone cannot. Black hole conjures exactly the right image. The absence of light, the depth of an opening with no bottom, the sense of irreversible falling. It is a name that earns its place, and as you drift towards sleep tonight, perhaps you can spare a quiet thought for the man who gave the universe's most dramatic objects their most perfect name. Before the term black hole took hold, these objects were sometimes called frozen stars. The name came from what a distant observer would actually see if they watched an object fall toward one. As the object approaches the event horizon, the light it emits becomes increasingly redshifted, stretched to longer and longer wavelengths by the extreme gravity, and the rate at which it appears to move slows dramatically due to gravitational time dilation. To a distant observer, the infalling object never quite reaches the event horizon. It appears to slow and slow and slow, its image growing dimmer and redder, hovering just above the boundary forever, frozen apparently at the edge of oblivion. It never disappears completely, it just fades asymptotically toward invisibility. From that perspective, the object looks like a star that has frozen at the moment of its collapse, a ghost of a star, preserved in amber at the threshold of the event horizon, dimming with infinite patience. This is not what the infalling object itself experiences. From its own perspective, it crosses the event horizon in finite time, feeling nothing dramatic at the boundary. But from the outside, looking in, you never quite see it go. You see it stop. You see it fade. You see it become a shadow of itself, suspended at the edge of the impossible. The universe in this way keeps its secrets gently. The things that fall past the event horizon do not vanish with a bang. They simply dim and become invisible. The way of fates fades when sleep finally takes you softly into the dark. Black holes can form in several ways, and the most common is the death of a massive star. When a star much more massive than our sun, at least 20 times the sun's mass, though many black hole-forming stars are far more massive than that, exhausts the nuclear fuel in its core. It loses the outward pressure that has been holding it up against gravity for millions of years. The core collapses in a fraction of a second, from a ball of iron larger than the Earth to a sphere just a few kilometers across. The collapse releases an enormous amount of gravitational energy, which blows the outer layers of the star outward in a spectacular explosion called a supernova. And what remains at the center, if the core is massive enough, is a black hole. It happens fast. The collapse itself takes less than a second. A star that has been burning for millions of years disappears in less time than a heartbeat. What remains is not the star anymore. The star is gone, dispersed into the surrounding space by the supernova explosion, enriching the interstellar medium with heavy elements that will one day become part of new stars and planets and oceans and living things. What remains is something new, something that was not there before. A singularity wrapped in an event horizon, bending space around it, waiting in silence for whatever comes next. A star that became something stranger than a star. A light that became the deepest darkness. A black hole is not a cosmic vacuum cleaner. This is one of the most persistent misconceptions about them, and it is worth setting gently aside. A black hole does not suck. It does not reach out across space and hoover up everything in its vicinity. It attracts matter gravitationally, but so does every other massive object in the universe. If you replace the sun tomorrow with a black hole of exactly the same mass, the Earth would not be pulled in. The planets would continue to orbit in exactly the same paths they follow today. The gravity would be identical. Same mass, same distance, same gravitational pull. Nothing would change except that there would no longer be sunlight. The danger of a black hole is not that it is hungry or reaching. The danger is proximity. If you venture close enough within the event horizon, there is no return. But from a safe distance, a black hole is simply another gravitating object, obeying the same laws as stars and planets and moons. The solar system is gravitationally safe from the black hole at the center of the Milky Way, which is about 26,000 light-years away. Its gravity at that distance is negligible. We orbit the galactic center slowly, peacefully, along with hundreds of billions of other stars, none of us in any danger from Sagittarius A. Black holes are dramatic at close range. At a distance, they are simply another feature of the landscape, massive, quiet, patient, and indifferent. Like a mountain visible on the horizon, present, impressive, and perfectly harmless from where you stand. Stellar black holes, the kind formed from the collapse of massive stars, are the most common type in the universe. They range in mass from about 3 times the mass of the Sun up to perhaps 100 solar masses, though some may be larger. Below 3 solar masses, the collapsed core becomes something else, a neutron star, an extraordinarily dense ball of neutrons held up by quantum pressure rather than collapsing into a singularity. Above that threshold, nothing can stop the collapse. Gravity wins completely. The core becomes a black hole. Stellar black holes are scattered throughout galaxies like seeds in a field. The Milky Way alone is estimated to contain between 10 million and 1 billion of them. The wide range reflecting how uncertain our count is. Since black holes that are not actively accreting matter are essentially invisible, we can only detect them when they are doing something, pulling gas from a companion star, bending the light of background stars through gravitational lensing, or merging with another compact object and sending gravitational waves rippling through space-time. But they are there, quiet and dark, woven into the fabric of the galaxy. Some of them are ancient remnants of the first generation of massive stars that lived and died in the early universe billions of years before the Earth existed. Others are younger, formed from stars that have only recently died. The Milky Way's history is written partly in its black holes, a census of every massive star that has ever lived and collapsed, preserved in the darkness as silent, patient gravitational monuments. Supermassive black holes are in a category entirely their own. Objects so massive, so vast in their gravitational reach, that the word enormous does not begin to do them justice. They sit at the centers of most large galaxies, including our own Milky Way, and they range in mass from millions to tens of billions of times the mass of the Sun. The one at the center of our galaxy, Sagittarius A, is about 4 million solar masses, a number that sounds large but is actually modest by the standards of supermassive black holes. Others are far more extreme. The black hole at the center of the galaxy, Messier 87, the first black hole ever imaged, is about 6.5 billion solar masses. TON 618, a quasar in the constellation Canes Venatici, harbors a black hole of roughly 66 billion solar masses. How these objects formed is still not fully understood. They are too massive to have simply accumulated mass from ordinary stellar collapse over the age of the universe. They must have either started from unusually massive seeds, perhaps direct collapse black holes formed from the collapse of enormous gas clouds in the early universe, or grown extraordinarily rapidly in the early universe when gas was more abundant and dense. Or perhaps both. The origin of supermassive black holes is one of the most active and fascinating open questions in modern astrophysics. But their existence is beyond doubt. They are there, anchoring galaxies, shaping their evolution, occasionally blazing as quasars with the light of trillions of suns. The quiet monarchs at the center of everything, intermediate black holes, occupy the middle ground between stellar and supermassive, objects of hundreds to thousands, perhaps tens of thousands of solar masses. They are the most elusive members of the black hole family. For decades, astronomers were not even sure they existed. Stellar black holes form readily from dying stars. Supermassive black holes announce themselves through the activity at galactic centers. But intermediate black holes, if they exist, would sit in a no-man's land, too large to form from a single star and too small to dominate a galactic nucleus. Evidence for them has been building gradually through observations of unusually bright X-ray sources in nearby galaxies called ultraluminous X-ray sources, through gravitational wave detections of unexpectedly massive mergers, and through the behavior of stars near the centers of some globular clusters. But definitive, unambiguous detection of an intermediate mass black hole remains elusive. They may be the missing link in our understanding of how supermassive black holes grow, perhaps starting as intermediate objects in the dense environments of early galaxies and then growing by, merging and accreting over billions of years. Or they may form through the runaway merging of stars in dense star clusters. The universe likely has a continuous spectrum of black hole masses from a few solar masses to tens of billions, with intermediate black holes filling the gap. We are still learning to see them. Primordial black holes are perhaps the most exotic members of the black hole family. Objects that, if they exist, were not born from dying stars or collapsing gas clouds, but from the extreme density fluctuations of the very early universe within the first fractions of a second after the Big Bang, in the hot, dense, rapidly expanding early cosmos. Regions that were slightly denser than average could, in principle, have collapsed under their own gravity before the expansion could smooth them out, creating black holes directly from the primordial plasma, without any stellar intermediate. The masses of primordial black holes would depend on when they formed. The earlier they formed, the smaller they would be, ranging potentially from microscopic to stellar mass scales. Primordial black holes have attracted intense interest in recent years as a candidate for dark matter, the invisible substance that makes up about 27% of the universe's energy content. If primordial black holes of a certain mass range were produced in sufficient numbers in the early universe, they could account for some or all of the dark matter without requiring any new fundamental particles. This possibility has driven extensive observational searches, looking for gravitational lensing of background stars, for gravitational wave signals from primordial black hole mergers, for other signatures. So far, the evidence is ambiguous, but the possibility remains open, tantalizing, and deeply interesting. A universe whose dark matter is not an undiscovered particle, but a collection of ancient, invisible black holes formed in the first heartbeat of creation, is a strange and beautiful possibility. The smallest theoretically possible black hole is an object of almost unimaginable contrast, something with the mass of a large mountain compressed into a space smaller than an atom. Such an object would have a Schwarzschild radius, an event horizon of about 10 squared meters, which is vastly smaller than a proton. The proton itself is about 10 meters across, already absurdly small by everyday standards. A primordial black hole of this size would be 10 billion times smaller still. and yet it would have a mass of roughly 1 billion metric tons, the mass of a mountain, concentrated into a space that makes atomic nuclei look fast. This is the Planck mass scale, the point at which quantum effects and gravitational effects are equally important, where the physics of general relativity and the physics of quantum mechanics are both essential and neither is adequate alone. A black hole this small would be intensely hot, blazing with Hawking radiation, and would evaporate almost instantaneously, in a fraction of a second, in a burst of energy. It would never be stable. It would be born and die before the universe had time to register its existence. Whether such objects ever formed or could form is a question tied to the deepest issues in quantum gravity, but the image itself is extraordinary. A black hole smaller than an atom, more massive than a mountain, burning briefly and brilliantly in a space too small to see. The universe, at its extremes, is never short of wonders. Sagittarius A, the supermassive black hole at the center of the Milky Way, has a mass of approximately 4 million times that of the Sun. 4 million suns, packed into a region of space about the size of the distance between Mercury and the Sun, roughly 44 million kilometers across. By the standards of supermassive black holes, this is actually quite modest. M87, the black hole at the center of the galaxy Messier 87, is about 1,600 times more massive. Tane 618 is over 16,000 times more massive. But Sagittarius A is ours. It is the black hole that anchors our galaxy, around which the entire Milky Way, all its hundreds of billions of stars, all its gas clouds and nebulae, its spiral arms and dark matter halo, orbits slowly and majestically over hundreds of millions of years. Our Sun takes about 225 to 250 million years to complete one orbit of the galactic center. In the entire history of the Earth, the solar system has completed only about 20 orbits around Sagittarius A. The dinosaurs were alive during the last orbit but one. The first multicellular life appeared only a few orbits ago. The universe is old and the galaxy is slow, and at its center, quiet and dark and patient, the black hole simply waits. It is currently in a low activity state, not feeding significantly, not blazing as a quasar, just present, massive spending space around it in its patient, permanent way, the still point at the center of everything we call home. Despite its mass of 4 million suns, the event horizon of Sagittarius A is only about 24 million kilometers in diameter, roughly the size of Mercury's orbit around the Sun. To appreciate how extraordinary this is, consider that the Sun, which is also quite compact for its mass, has a diameter of about 1.4 million kilometers. Sagittarius A, 4 million times more massive, has an event horizon only about 17 times wider than the Sun. All that mass in such a small space, the density implied is staggering. Of course, as we will discuss later, the concept of density breaks down at the singularity itself. But even averaging the mass over the volume enclosed by the event horizon, the density of Sagittarius A is several trillion times that of water. These numbers stretch the imagination past its comfortable limits. But there is something calming about simply sitting with them without trying too hard to grasp them. The universe is extreme in ways that human intuition was not built to accommodate. Our intuition evolved on the African savanna, dealing with objects the size of antelopes and distances the width of a valley. It was never designed to handle 4 million solar masses compressed inside Mercury's orbital radius, and yet here we are, human minds lying in the dark, reaching out toward these impossible scales with the only tools we have. Curiosity, patience, mathematics, and a willingness to be astonished. The largest known black hole in the observable universe is a monster called Photon 618, residing at the center of a quasar, an extraordinarily luminous galactic nucleus, located about 10.4 billion light-years away from Earth in the constellation Canes Venatici, Its mass is approximately 66 billion times the mass of the Sun. 66 billion suns compacted into a region of space. The event horizon of TON 618 is enormous. Its Schwarzschild radius is about 1,300 astronomical units, meaning its event horizon is about 1,300 times the distance from the Earth to the Sun. Our entire solar system, from the Sun to the outermost reaches of the Kuiper Belt, fits comfortably inside it, with room to spare. The Sun is 8 light minutes from Earth. The event horizon of TON 618 is about 7.5 light days across, standing on an imaginary platform at the edge of its event horizon. If such a thing were possible, you would see the bright accretion disk curling around you in every direction. Lit by the ferocious energy of infalling matter, you would see the distant universe distorted into rings and arcs by the extreme gravitational lensing. And the tidal forces at this vast scale would be gentle enough that you could cross the event horizon without being torn apart. You would simply drift inward. The boundary of no return would pass over you quietly and completely, and all the universe you had ever known would be, from that moment, behind you. Unreachable, preserved only in memory and in the light still falling after you. If you compressed the Sun into a black hole, squeezing all its mass into a sphere small enough that not even light could escape, the resulting black hole would be only about 6 kilometers in diameter, about the size of a small city. The Sun's mass is about 2 times 10 to the power of 30 kilograms, a truly astronomical number. And yet, if you packed all of that into a sphere just 6 kilometers across, gravity at its surface would become so extreme that the escape velocity would exceed the speed of light. The threshold would have been crossed. The event horizon would form. The Sun would become, in that hypothetical compression, a black hole. Of course, the Sun will never actually do this. It is not nearly massive enough. When the Sun reaches the end of its life in about 5 billion years, it will expand into a red giant, shed its outer layers, and leave behind a white dwarf, a dense but not extreme stellar remnant, roughly the size of Earth. Only stars at least about 20 times more massive than the Sun end their lives as black holes. But the exercise of imagining the Sun compressed to 6 kilometers is useful. It makes the relationship between mass and event horizon size concrete and vivid. 6 kilometers, a distance you could walk in an hour, containing the mass of an entire star. The universe, in its extremes, is not shy about packing enormous things into very small spaces. Breathe slowly and let that strangeness settle gently over you. The Earth, too, has its own Schwarzschild radius, the size it would need to be compressed to in order for it to become a black hole. For the Earth, that radius is about 9 millimeters, less than a centimeter, the entire mass of our planet, all 6 times 10 to the power of 24 kilograms of it. All the iron and nickel and rock and ocean and atmosphere and every living thing that has ever existed on its surface would need to be squeezed into a sphere about the size of a marble. If you could do that, if some unimaginable force could compress the Earth to that density, the escape velocity at the surface would exceed the speed of light, and the Earth would become a black hole. Everything on its surface would fall in. Everything around it would eventually feel the same gravitational pull as before. The Moon would continue to orbit. The Sun would hold the former Earth in its annual path, but there would be no light, no warmth, no air, no ocean, no birdsong, just a marble-sized singularity, utterly dark, utterly silent, bending space around it in perfect, absolute gravity. And then, over time, over an almost inconceivably long time, it would very slowly evaporate through Hawking radiation, growing slightly warmer as it shrank, until in a final flash it was gone. All of Earth's matter, all of Earth's history released back into the universe as radiation. Transformed entirely, nothing wasted, just changed. Black holes can spin. Not all of them spin at the same rate. Some rotate slowly, and some approach the maximum possible spin allowed by the laws of physics. A rotating black hole is described by a different mathematical solution to Einstein's equations than a non-rotating one. The non-rotating case is called a Schwarzschild black hole, described by Carl Schwarzschild in 1916. The rotating case is called a Kerr black hole, described by the New Zealand mathematician Roy Kerr in 1963. Kerr's solution was one of the great mathematical achievements in the history of general relativity, a beautiful, exact solution describing the space-time geometry around a spinning massive object. When a black hole spins, it drags space-time around with it, the way a spinning ball of honey drags the honey around it. This effect is called frame dragging, and it creates a region around the spinning black hole, outside the event horizon, called the ergosphere, within which space-time is dragged so forcefully that it is impossible for anything to remain stationary with respect to the distant universe. Everything in the ergosphere, no matter how powerful its engines, is forced to co-rotate with the black hole. It is a deeply strange property, the rotation of a black hole reaching out beyond its event horizon and pulling the fabric of space-time itself into motion. The universe, rotating, dragging, spinning. Even in the darkest and most extreme objects, there is always motion, always some slow, ancient turning. The ergosphere is the region surrounding a rotating black hole, outside the event horizon, where space-time is dragged so powerfully by the black hole's rotation that nothing can remain stationary. Within the ergosphere, every object, every particle, every photon, every hypothetical spacecraft is forced to move in the direction of the black hole's rotation, regardless of how much thrust is applied in the opposite direction. The rotation of space-time itself overrides any possible resistance. And yet, the ergosphere is outside the event horizon. Objects that enter the ergosphere can, in principle, escape. They are not yet past the point of no return. This leads to one of the most fascinating theoretical possibilities in all of black hole physics, a mechanism called the Penrose process, proposed by the British physicist Roger Penrose in 1969. In the Penrose process, an object entering the ergosphere could split into two parts, with one part falling into the black hole and the other escaping to infinity with more energy than the original object had. The extra energy comes from the rotational energy of the black hole itself. The black hole slows down very slightly in the process. In principle, the Penrose process could extract up to 29% of the total mass energy of a maximally rotating black hole. It is a theoretical power source of extraordinary efficiency, extracting energy from the rotation of space-time itself. No civilization has ever used it, but the universe may have. The relativistic jets launched from accreting black holes may draw their energy from mechanisms related to the Penrose process, powered by the spin of one of the most extreme objects in existence. Gravitational time dilation near a black hole is one of the most profound and mind-bending consequences of general relativity, and it is not merely theoretical, it is real, measurable, and experimentally confirmed. The basic idea is this: time passes more slowly in stronger gravitational fields. A clock at sea level on Earth ticks very slightly more slowly than a clock at the top of a mountain, because the gravitational field is very slightly stronger at sea level. The effect is tiny but measurable, and GPS satellites must correct for it or their positioning data would become inaccurate within minutes. Near a black hole, the effect is not tiny. Near a black hole, the effect is enormous. An astronaut hovering at a fixed distance just outside the event horizon of a black hole, kept there by some impossibly powerful engine fighting the gravity, would experience time passing at a dramatically slower rate than a distant observer. While the distant observer ages by a year, the near-horizon astronaut might age only by minutes. Closer still, and the ratio becomes more extreme. At the event horizon itself, time dilation becomes infinite, From the perspective of the distant observer, time at the event horizon appears to stop completely. This is related to the frozen star appearance we discussed earlier. The infalling object appears frozen at the horizon because its time, from our perspective, has slowed to a standstill. Time near a black hole is not the steady, uniform river we experience in everyday life. It is a variable quantity, thickened and slowed by the presence of mass, and near enough to a black hole, it becomes something almost unrecognizable. Gravitational time dilation is not just a thought experiment or a mathematical curiosity. It is being measured. GPS satellites orbit at about 20,200 kilometers above Earth's surface, where Earth's gravitational field is weaker than at the surface. According to general relativity, clocks in that weaker field run faster than clocks at sea level by about 45 microseconds per day. At the same time, the satellites are moving very quickly, and special relativity predicts that moving clocks run slower by about 7 microseconds per day. The net effect is that GPS satellite clocks gain about 38 microseconds per day relative to clocks on the ground. That sounds tiny, but the speed of light is about 30 centimeters per nanosecond. If GPS systems did not correct for this relativistic effect, the positioning errors would accumulate at about 10 kilometers per day. Your phone's GPS would be useless within hours. Every time you use navigation on your phone, you are, in a small and practical way, relying on Einstein's general theory of relativity, the same theory that describes the time dilation near a black hole. The universe operates by one consistent set of rules, from the gentle curves of Earth's gravity to the extreme geometry near an event horizon. Time really does slow down near massive objects, not metaphorically, not approximately, really, and near a black hole that slowing becomes absolute. If you fell into a stellar black hole, one of relatively modest mass, a few dozen times the mass of the Sun, you would not survive to reach the event horizon. The tidal forces would destroy you first. Tidal forces arise from the difference in gravitational pull across the extent of your body. The part of you closer to the black hole would be pulled more strongly than the part farther away. Your body would be stretched, very gently at first, then with rapidly increasing force, in the direction toward the singularity, while being simultaneously compressed from the sides. This stretching and compression is called spaghettification, which is one of the most evocative technical terms in all of physics. You would be lengthened into a long, thin strand of matter, like taffy being pulled, like pasta being rolled out. For a stellar black hole, this process would begin well outside the event horizon, at a distance of thousands of kilometers, and would be fatal long before you cross the point of no return. For a supermassive black hole, however, the tidal forces at the event horizon are much gentler. The event horizon is so large, and the gradient of gravity so gradual at that scale, that you could cross it intact. You would feel nothing unusual at the moment of crossing. You would simply be inside. And then, gradually, as you fell deeper toward the singularity, the tidal forces would intensify. Even for a supermassive black hole, spaghettification would eventually claim you, just much farther inside than for a smaller one. The universe is patient in its extremes. Gravitational lensing, the bending of light by gravity, is one of the most visually spectacular predictions of general relativity, and near a black hole it reaches its most extreme expression. Light, despite having no mass, follows the curvature of space-time just as matter does. And near a black hole, space-time is so deeply curved that light can be bent into tight arcs, loops, and even complete circles. At a specific distance from a black hole, called the photon sphere, the curvature is so precise that light can orbit in perfect circles, traveling endlessly around the black hole without either falling in or escaping. For a non-rotating black hole, the photon sphere sits at 1.5 times the Schwarzschild radius, just outside the event horizon. Within the photon sphere, all circular photon orbits are unstable. Any perturbation will cause the light to either fall inward or spiral outward. But right at that radius, for a brief moment in each photon's history, it travels in a perfect circle, and this creates the bright ring you see in photographs of black holes. The photon ring, the glowing circle of light at the edge of the black hole's shadow. Every photon in that ring has orbited the black hole at least once, sometimes many times, before escaping to your detector or your eye. You are seeing light that has traveled in circles around one of the most extreme objects in the universe. The universe at its most extreme is also one of its most beautiful. At the photon sphere of a black hole, that precise distance where light can orbit in perfect circles, you would be able, in principle, to see the back of your own head. This is not a metaphor or a poetic image. It follows directly from the geometry of space-time at that location. Light from the back of your head, traveling outward in the direction away from you, would be bent by the black hole's gravity into a complete circle, traveling all the way around and arriving at your eyes from the front. You would see yourself from behind, your hair, the back of your neck, your shoulders, all visible directly in front of you, and not just once. The light could loop multiple times, creating additional images at different angles, like the infinite reflections you see in a barbershop between two facing mirrors. The photon sphere is the place where the universe's most extreme geometry creates the most extreme visual experience. Looking outward from the photon sphere, you would see the entire outside universe compressed into a bright, distorted ring above the black hole's shadow. All the stars and galaxies of the cosmos squashed into a circle by the gravitational lensing, and looking slightly inward, you would see the black hole's shadow, pure, absolute darkness, with no photons escaping from beyond the event horizon. The boundary between everything and nothing, between light and the permanent dark. Close your eyes now. Let that image dissolve into the gentler dark behind your eyelids. The no-hair theorem is one of the most elegant and surprising results in all of black hole physics. It states that a black hole, no matter how it formed, can be completely described by just three numbers: its mass, its angular momentum, spin, and its electric charge. That is all. Nothing else. It doesn't matter whether the black hole formed from a star or a gas cloud or a collection of old textbooks. It doesn't matter what the temperature of the material was, what elements it was made of, whether it had a magnetic field, whether it was rotating clockwise or counterclockwise, whether it was made of matter or antimatter. Once the material has fallen past the event horizon, all that information is lost, or at least inaccessible to the outside universe. Only mass, spin, and charge remain, imprinted on the geometry of space-time around the black hole. All the complexity of everything that fell in, all the structure, all the chemistry, all the history is reduced to three numbers. The universe, past the event horizon, performs the ultimate simplification. It takes the infinite variety of the physical world and distills it down to its most essential properties. This theorem was developed in the 1960s and 1970s by John Wheeler, Brandon Carter, Stephen Hawking, and others, and it is one of the most striking results in theoretical physics. Three numbers, everything else gone. The universe, at its most extreme, chooses simplicity. Hawking radiation is the name given to the faint, quantum mechanical glow that Stephen Hawking proposed in 1974 that black holes should emit. It was a revolutionary and deeply counterintuitive idea. The proposal that black holes, the ultimate darkness, the objects from which nothing can escape, are in fact not perfectly black. They glow, very faintly, very coldly, but they glow. The mechanism Hawking proposed involves the quantum vacuum, the fact that empty space is not truly empty, but is filled with pairs of virtual particles that spontaneously appear and annihilate each other, over timescales so short they are below the threshold of direct measurement. Near the event horizon, one particle of such a pair can fall inside the black hole. while the other escapes outward to a distant observer. The escaping particle appears to be radiation emitted by the black hole. And because energy must be conserved, the black hole loses a tiny amount of mass each time this happens. Hawking radiation is real. It follows from combining quantum field theory with general relativity in a careful and mathematically rigorous way. But it is extraordinarily faint for large black holes. The temperature of Hawking radiation from a stellar black hole is a fraction of a billionth of a degree above absolute zero, orders of magnitude colder than the cosmic microwave background. We cannot detect it directly, but Hawking was almost certainly right, and the implications of his insight ripple through theoretical physics to this day. Stephen Hawking's proposal that black holes emit radiation, that they glow faintly with a quantum mechanical luminosity inversely related to their mass, carries a remarkable consequence. The smaller the black hole, the hotter and more intense the Hawking radiation. This is the opposite of what you might intuitively expect. Larger black holes have more mass and more gravity, so you might think they would emit more powerfully, but the relationship runs the other way. A stellar black hole with a mass of 10 suns has a Hawking temperature of about 6 billionths of a degree above absolute zeros, essentially undetectable. A black hole the mass of a mountain, far smaller, would have a Hawking temperature of billions of degrees and would glow as brightly as a nuclear reactor. A black hole the mass of a paperclip would be so hot that its Hawking radiation would have the energy of a nuclear bomb. And a black hole at the Planck mass, the absolute minimum, would evaporate instantaneously in a burst of energy so intense it would be, by weight, the most energetic explosion possible. This inverse relationship between mass and Hawking temperature is one of the strangest properties of black holes. The smaller they get, the hotter they burn. The lighter they become, the more violently they end. A dying black hole goes out, not with a quiet fade, but with a final, fierce, brilliant flash. The universe's smallest and most dramatic last act. Over an almost incomprehensibly long stretch of time, Hawking radiation causes black holes to slowly lose mass and eventually evaporate entirely. For a stellar black hole of about 10 solar masses, the time required to evaporate completely, losing all its mass through the steady trickle of Hawking radiation, is approximately 2 times 10 to the power of 67 years. That is a 2 followed by 67 zeros. The current age of the universe is about 13.8 billion years, 1.38 times 10 to the power of 10. The evaporation time of a stellar black hole is therefore about 10 to the power of 57 times the current age of the universe. A number so vast it has no meaning in ordinary experience. The universe would have to last almost forever, and then last that long again, many times over. For a stellar black hole to evaporate, for a supermassive black hole of a billion solar masses, the evaporation time is even larger, roughly 10 to the power of 83 years. These are numbers that transcend imagination. They speak to a future so remote that all the stars will have burned out long before. All the galaxies will have gone dark. All the planets will have been swallowed or flung into the void. In the far future of the universe, there may be a time when the only things left are black holes and the cold, dark sea of expanding space. And then, one by one, over those unimaginable timescales, the black holes too will fade. And the universe will be left in a final, perfect, permanent silence, as a black hole shrinks through Hawking radiation, slowly losing mass over astronomical timescales. Something extraordinary happens in its final moments. As the mass decreases, the Hawking temperature increases. As the temperature increases, the radiation becomes more intense, which causes the mass to decrease faster, which increases the temperature further. It is a feedback loop that accelerates toward a dramatic conclusion. In the final fraction of a second of a black hole's life, as it approaches zero mass, the temperature and luminosity diverge toward infinity. The last moments of a black hole are not a quiet fading. They are a final, explosive burst of energy, a flash of radiation across all wavelengths. A brief moment of extraordinary luminosity from a point in space where a singularity had existed, perhaps for billions or trillions of years. After this flash, the black hole is gone. There is no singularity anymore. There is no event horizon. There is nothing, or rather, there is just the radiation it emitted, spreading outward at the speed of light, carrying away the last of its mass energy in the form of photons and other particles. Whether any information about the original contents of the black hole is encoded in this final burst is the subject of the information paradox, one of the deepest unresolved questions in theoretical physics. But the image of the ending is beautiful in its own right. A black hole born from the death of a star, living for timescales beyond imagination, ending in one final, bright, brief moment of light. The black hole information paradox is perhaps the deepest puzzle currently facing theoretical physics. It arises from a conflict between two of our most fundamental theories, general relativity and quantum mechanics. General relativity predicts that anything that falls into a black hole is lost forever, trapped behind the event horizon, pulled inevitably toward the singularity, sealed away from the outside universe. Quantum mechanics, however, insists that information can never be truly destroyed. The laws of quantum mechanics are reversible. In principle, if you know the complete quantum state of a system at any moment, you can calculate what it was doing at any point in the past. Information is always preserved. These two principles are in direct conflict when applied to black holes. If a black hole swallows a library of books and then evaporates completely through Hawking radiation, where does the information in those books go? Hawking's original calculation suggested that Hawking radiation is completely random. It carries no information about what fell into the black hole. If that is correct, the information is genuinely destroyed and quantum mechanics is violated. If quantum mechanics is correct, the information must somehow be encoded in the radiation. But how? Given that the radiation seems to arise only from the region just outside the event horizon, far from where the books ended up, the paradox has driven some of the most creative theoretical physics of the last 50 years, and it remains unresolved. But it has been enormously productive, pointing the way toward quantum gravity, holography, and some of the deepest ideas about the nature of information and reality. One proposed resolution to the black hole information paradox involves an idea called the firewall, proposed in 2012 by physicists Ahmed Al-Maheri, Donald Murrow, Joseph Polchinski, and James Sully, sometimes called the ANPS team. The firewall hypothesis suggests that the event horizon of a black hole is not the gentle, unremarkable boundary that general relativity describes. Instead, it proposes that the event horizon is surrounded by a wall of high-energy radiation, a firewall that would instantly destroy anything that crossed it. The firewall hypothesis was motivated by a careful analysis of the quantum entanglement between Hawking radiation emitted at different times. If information is preserved in Hawking radiation, then late-time radiation must be entangled with earlier radiation. But quantum mechanics also requires that radiation emitted just outside the event horizon be entangled with its partner particle just inside. You cannot have both entanglements simultaneously. Quantum mechanics forbids a particle from being maximally entangled with two different things at once. Something must give. The firewall is one way to resolve this conflict, by breaking the entanglement at the horizon, but at the cost of the horizon becoming a violent, destructive barrier. General relativity says the event horizon is smooth and unremarkable. Quantum mechanics, carefully analyzed, may say otherwise. The conflict between these two predictions is one of the sharpest formulations of the tension between our two greatest theories of physics. Something is wrong. We just don't yet know what. The holographic principle is one of the most radical and beautiful ideas in modern theoretical physics, and it offers a possible resolution to the information paradox. It proposes that all the information contained within a volume of space can be completely described by information encoded on the boundary surface of that volume, like a two-dimensional hologram that contains all the information needed to reconstruct a three-dimensional image applied to black holes. The holographic principle suggests that all the information about everything that has ever fallen into a black hole is encoded on its event horizon. That two-dimensional surface in space-time, the three-dimensional contents of the black hole's interior are, in this picture, a kind of holographic projection of information stored on the horizon. This means information is not lost when things fall in. It is simply encoded in a different form on the horizon, and eventually released as Hawking radiation carries that encoded information back out. The holographic principle emerged from string theory and was developed in the 1990s by Gerard Hooft, Leonard Susskind, and others. It received powerful theoretical support from Juan Maldaceno's discovery in 1997 of the ADES/CFT correspondence, a precise mathematical duality between a theory of gravity in a certain space and a quantum field theory on its boundary. The universe may be, at its deepest level, a hologram, not in the science fiction sense, but in the profound mathematical sense that the information in any region of space is fully captured by its surface. The inside is contained in the edge. The volume is written on the boundary. Rest on that image as you drift towards sleep. In 2022, a theoretical breakthrough offered a partial resolution to the black hole information paradox through an approach called the island formula, proposed by a group of physicists using techniques from the ADES/CFT correspondence. The island formula is a new way of calculating the entropy, the information content of Hawking radiation over the lifetime of a black hole. What it found was extraordinary. When you calculate the entropy of Hawking radiation using this new formula, accounting for contributions from certain regions inside the black hole called islands, the entropy of the radiation follows the expected quantum mechanical curve, rising at first as the black hole evaporates, and then falling back down after a certain point called the page time. This is exactly what you would expect if information is preserved and eventually returned through the radiation. The island formula does not fully explain the mechanism by which information escapes. It does not tell you how the information gets encoded in the radiation, but it strongly suggests that information is preserved and that quantum mechanics is not violated. It is a major step forward, though much work remains. The information paradox is not fully resolved, but the shore is now visible. The island formula is a bridge, partial, tentative, but real, between our current theories and the deeper understanding that still awaits. One day, perhaps, the full theory of quantum gravity will make the mechanism clear, and we will understand at last what the universe does with the things it swallows. The information paradox is not just a puzzle about black holes. It is a window into the deepest tensions in all of physics, a place where quantum mechanics, general relativity, and thermodynamics all come into conflict, and none of them gives way gracefully. Quantum mechanics is the theory of the very small, of particles and their interactions, of probability and measurement, of the fundamental discreteness of energy. General relativity is the theory of the very large and the very massive, of curved space-time, of gravity, of the large-scale structure of the universe. These two theories are the twin pillars of modern physics, and each is extraordinarily successful in its own domain, but they are deeply incompatible at a fundamental level. Quantum mechanics describes a world of discrete energy levels, of uncertainty, of non-locality. General relativity describes a smooth, continuous space-time, deterministic in its geometry. At the singularity of a black hole and at the moment of the Big Bang, both theories are simultaneously required and neither is adequate. The information paradox is one of the clearest and most precise ways in which this incompatibility manifests, and resolving it will almost certainly require a new theory, quantum gravity, that supersedes both and reveals the deep reality from which both emerge as approximations. We are living at a time when the foundations of physics are still being laid. The deepest laws of the universe are still, in an important sense, unknown. And that is one of the most exciting facts about the age we live in. The first photograph ever taken of a black hole, or rather, of the shadow of a black hole surrounded by its glowing accretion disk, was released to the world on April 10, 2019. It showed M87, the supermassive black hole at the center of the galaxy Messier 87, about 55 million light-years away. The image, a fuzzy orange-red ring of light surrounding a dark central region, was, by any measure, one of the most important photographs in the history of science. It confirmed, directly and visually, a prediction that had stood in the mathematics of general relativity for over a century. There, in that image, was the shadow of the event horizon, the absence of light from a region where light cannot escape, surrounded by the glow of superheated plasma spiraling inward. The bright ring is not uniform. One side is brighter than the other, because the plasma on the side moving toward us is Doppler boosted, its light enhanced, while the plasma on the receding side is dimmed. The image matched theoretical predictions with extraordinary precision. The Event Horizon Telescope collaboration, involving over 200 scientists from 20 countries and 13 institutions, had linked radio observatories across the planet in Hawaii, Chile, Arizona, Spain, Mexico, the South Pole, into a single Earth-sized virtual telescope and used it to photograph a black hole. It was one of the great collaborative events of science, a species that learned to use tools a few million years ago, that built its first cities 10,000 years ago, that only discovered radio waves 130 years ago, photographed the edge of infinity, and it was beautiful. On May 12, 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A, the black hole at the center of our own Milky Way. This achievement was in some ways even more difficult than imaging M87. While M87 is vastly farther away, it is also vastly larger and more massive, and the plasma orbiting it moves on timescales of weeks, allowing long exposure observations to be averaged cleanly. Sagittarius R, being much smaller, has plasma that completes an orbit in just minutes, the equivalent of trying to photograph a child spinning wildly on a merry-go-round versus a slow-moving ocean liner. The gas around Sagittarius A changes its configuration rapidly, producing blurring and noise in the image that required sophisticated new analysis techniques to overcome. The resulting image was nonetheless remarkable. A glowing ring of orange light, similar in character to the M87 image but with a slightly different structure. The shadow in the center is the region within which the event horizon lies, the point of no return for our own galactic center. It is about 26,000 light-years away. The light in that image left its source before the last ice age began, before modern humans had spread across the planet, when our ancestors were still learning to make sophisticated tools and perhaps beginning to tell each other stories in firelight. And the light traveled all that way to reach us, to be caught in our antennas, to show us the face of the black hole that anchors our galaxy. Gravitational waves, ripples in the fabric of space-time caused by the acceleration of massive objects, were predicted by Einstein in 1916, a year after publishing his general theory of relativity. He predicted them, but doubted they would ever be measurable. They seemed too small, too faint, too diluted by the time they traveled any significant distance. He was wrong. On September 14, 2015, the LIGO detector, the Laser Interferometer Gravitational Wave Observatory, detected gravitational waves for the first time. The signal came from the merger of two black holes, each roughly 30 solar masses, located about 1.3 billion light-years away. As the two black holes spiraled together and merged, they released energy equivalent to 3 solar masses in the form of gravitational waves, pure ripples in space-time, traveling outward at the speed of light. By the time those waves reached Earth, the stretching and squeezing of space they caused was smaller than 1/10,000th the diameter of a proton. And LIGO measured it. The experiment is one of the greatest engineering achievements in human history. A pair of L-shaped tunnels, each 4 kilometers long, bouncing laser light to detect displacements smaller than an atomic nucleus. When the signal was first identified, the scientists did not believe it. They checked for instrumental glitches, for equipment malfunctions, for any alternative explanation. There was none. The universe had spoken, and we had finally learned to listen to its deepest voice. Since the first detection of gravitational waves from a black hole merger in 2015, dozens of such events have been recorded by the LIGO and Virgo detectors. Each detection is a story, 2 black holes that formed billions of years ago, perhaps in the same stellar binary system, perhaps captured into orbit around each other by gravitational interactions, spiraling slowly inward over millions or billions of years as they radiated gravitational energy, finally merging in a fraction of a second and releasing a burst of space-time ripples that crossed the universe to reach our detectors. Each merger carries information about the masses, spins, and distances of the black holes involved. By studying the population of detected mergers, astrophysicists are building up a picture of how black holes form, how massive they can be, how their properties depend on the environments in which their parent stars lived. Some detected mergers have involved black holes of unexpectedly high mass, larger than models of stellar evolution predict can form from individual star deaths. These may be the long-sought intermediate mass black holes forming through previous merger events. Black holes that grew by absorbing other black holes, building up mass generation by generation. Each detection adds a data point to a new kind of astronomy, gravitational wave astronomy, a way of observing the universe that does not use light at all, but listens instead to the vibrations of space-time itself. We have given the universe a new sense with which to observe itself, and the universe, obligingly, has been remarkably forthcoming. The relationship between supermassive black holes and their host galaxies is one of the most striking and still partially mysterious correlations in all of astrophysics. Observations over the past 3 decades have revealed that the mass of the central black hole in a galaxy is tightly correlated with the properties of the galaxy's central bulge, particularly the velocity dispersion of its stars. More massive bulges harbor more massive black holes. The correlation is not approximate. It is remarkably tight, spanning 5 orders of magnitude in black hole mass, from millions to hundreds of billions of solar masses. This tight correlation suggests that black holes and galaxies do not grow independently. They co-evolve. Whatever process builds a galaxy also builds or regulates its central black hole, and the mechanism by which they communicate across such vast scales. The black holes sitting in a region perhaps a few light years across, regulating a galaxy that spans hundreds of thousands of light years, is thought to involve the feedback of energy from the accreting black hole. When a black hole is actively feeding, it releases enormous amounts of energy, heating the surrounding gas, driving powerful winds, launching relativistic jets. This energy can heat and disperse the gas from which new stars would form, effectively turning off star formation in the galaxy. The black hole, in this way, acts as a thermostat for its entire galaxy. It regulates the temperature of the gas. It controls the rate of star formation. It is not merely a passive resident of the galactic center. It is an active participant in the galaxy's entire evolutionary history. When a supermassive black hole is actively consuming large amounts of material, when gas and dust are falling into it in significant quantities, it becomes one of the most luminous objects in the perverse universe. This active state is called a quasar, from quasi-stellar object, and quasars were among the most puzzling astronomical discoveries of the 1960s. They appeared to be star-like points of light in the sky, but their spectra revealed that they were moving away from us at extraordinary velocities, meaning they were extraordinarily distant. And if they were that distant, their apparent brightness implied luminosities that seemed physically impossible. thousands of times more luminous than entire galaxies. The solution, which took years to establish, is that quasars are powered by supermassive black holes accreting at enormous rates. As infalling material spirals inward through an accretion disk, it heats up to millions of degrees and releases enormous amounts of energy, up to 40% of the mass energy of the accreting material, compared to the 0.7% that nuclear fusion in stars manages to release. A quasar, powered by a black hole accreting just a few solar masses of material per year, can outshine the combined light of 1 trillion stars. The most distant quasars are seen as they were when the universe was less than 1 billion years old. They tell us that supermassive black holes were already fully formed, already blazing with extraordinary luminosity. In the earliest epochs of cosmic history, their existence is one of the most challenging facts for our models of early universe structure formation. Some of the most dramatic structures associated with black holes are the relativistic jets, narrow beams of plasma and radiation launched from the polar regions of accreting black holes at speeds approaching the speed of light. These jets can extend for thousands, sometimes millions, of light years, far beyond the boundaries of the host galaxy, and they carry enormous amounts of energy into the surrounding intergalactic medium. The jet from M87 is particularly famous. It stretches about 5,000 light-years from the black hole and can be seen in radio, optical, and X-ray light. It was first observed by the astronomer Heber Curtis in 1918, who described seeing a curious straight ray extending from the nucleus of M87. He had no idea what it was. Today we know it is a beam of plasma, twisted and compressed by powerful magnetic fields and launched by the rotational energy of the spinning black hole and its accretion disk. The exact mechanism by which relativistic jets are launched is still being actively studied. The leading models involve the extraction of rotational energy from either the spinning black hole itself by the Blandford's-Narshek mechanism or the spinning inner edge of the accretion disk. Either way, the jet is a direct consequence of the extreme physics near the event horizon. Matter falling in, energy coming out, as a beam of particles and radiation that can travel for millions of years and reshape the environment of an entire galaxy. The black hole consumes, and then it creates black hole feedback. The energy released by a quasar or active galactic nucleus into its surrounding environment is one of the dominant processes shaping the large-scale structure of the universe. When a supermassive black hole is actively accreting, it releases energy in the form of radiation, winds, and jets. This energy heats the gas surrounding the black hole and, on larger scales, the gas filling the galaxy and even the intergalactic medium. Hot gas does not collapse easily under gravity, so the heating of gas by black hole feedback can suppress or entirely halt the formation of new stars. In this way, a black hole at the center of a galaxy can regulate the galaxy's own growth. Without feedback, computer simulations of galaxy formation predict that galaxies would form too many stars. They would be far larger and more massive than observed. Including black hole feedback brings the simulations into agreement with observations. The largest galaxies in the universe, the giant elliptical galaxies sitting at the centers of galaxy clusters, are thought to have had their star formation quenched by the feedback from their supermassive black holes billions of years ago. The black hole drained the energy from the gas, heated it away, and left behind a galaxy of old red stars, a galaxy that stopped growing. In a very real sense, the destiny of a galaxy is determined, in part, by the black hole it carries at its center. The darkness at the heart shapes the light that surrounds it. Sagittarius A, despite being the supermassive black hole at the center of our own galaxy, is currently in a remarkably quiet state. It is not accreting large amounts of material. It is not blazing as a quasar. It is not launching powerful jets. By the standards of active galactic nuclei across the universe, it is almost dormant, occasionally flaring briefly as a small amount of gas or dust falls in. but producing luminosity only a tiny fraction of what an active quasar would generate from a black hole of its mass. This relative quiescence makes Sagittarius A much harder to study than more distant but more active galactic nuclei because it produces so little radiation, but it also makes the Milky Way a much more hospitable place for life. An active quasar at the center of the galaxy would flood the surrounding stars with X-rays and gamma rays, potentially sterilizing or destabilizing planetary systems across a wide region. The quiet nature of our galactic center may be one of the reasons the Milky Way has been a good host for life. But it was not always so quiet. Evidence in the form of the Fermi bubbles. Vast lobes of gamma-ray emission extending 25,000 light-years above and below the galactic plane suggest that Sagittarius A was far more active a few million years ago. The bubbles are thought to be the remnants of a past episode of intense activity. A few million years ago, our galaxy's center blazed, and then it went quiet, and here we are in the silence that followed. The Fermi bubbles are two enormous lobes of gamma-ray and X-ray emission that extend above and below the plane of the Milky Way, each stretching about 25,000 light-years from the galactic center. Discovered in 2010 by the Fermi Gamma-Ray Space Telescope, they represent some of the most dramatic evidence that our galaxy's central black hole was not always as quiet as it is today. The leading explanation is that the bubbles are the remnants of a massive outburst from Sagittarius A that occurred somewhere between 1 and several million years ago, a relatively recent event in cosmic terms, happening long after the first humans were beginning to walk on the African savanna. During this outburst, which may have lasted for hundreds of thousands of years, Sagittarius A was accreting material at a much higher rate, possibly triggered by the infall of a large cloud of gas. The energy released was enormous, enough to drive a vast wind of plasma outward from the galactic center, inflating the bubbles that are still visible today, millions of years after the outburst ended. The bubbles are still expanding slowly, carrying the memory of an ancient activation. Looking up at the sky, if you could see gamma rays, you would see these two enormous structures, one above and one below the galactic plane, glowing softly in high-energy light, the fingerprints of a violence that ended before our species learned to speak, preserved still in the structure of the galaxy we call home. In approximately 4 billion years, the Milky Way and its nearest large galactic neighbor, the Andromeda Galaxy, M31, will collide and merge. This will be an extraordinary event in the history of the universe, though not a violent one in the everyday sense. The stars in both galaxies are so widely spaced that very few individual stars will physically collide. Instead, the two galaxies will pass through each other, their gravitational forces distorting both into long tidal streams and arcs, before settling over hundreds of millions of years into a single, larger elliptical galaxy. But at the centers of each galaxy, there is a supermassive black hole, Sagittarius A in the Milky Way, weighing 4 million solar masses, a black hole of comparable or larger mass at the center of Andromeda. These two black holes, as their host galaxies merge, will gradually be brought closer together, first by the dynamical friction of the surrounding stars, then, in the final stages, by the emission of gravitational waves as they spiral tighter and tighter. Eventually, after perhaps hundreds of millions of years following the initial galactic merger, the two black holes will reach a separation close enough for gravitational wave emission to drive them rapidly together. They will merge in a final burst of gravitational waves, the most energetic event in the local universe since the Big Bang, and form a single, more massive supermassive black hole at the center of the merged galaxy. A quiet end, a patient end, billions of years in the making. Long after the last star in the solar system has gone cold, the Einstein-Rosen bridge, better known as a wormhole, is a theoretical structure in general relativity that connects two separate regions of space-time, like a tunnel through the fabric of the universe. It was first described mathematically by Einstein and his colleague Nathan Rosen in 1935 as a mathematical curiosity arising from the equations of general relativity in its simplest form. An Einstein-Rosen bridge connects the interior of a black hole in one region of space to the interior of a white hole, a hypothetical object that only expels matter in another region. The problem is that this kind of wormhole is not traversable. It appears and pinches off faster than anything could travel through it, even light. A traversable wormhole, one through which you could actually pass and emerge somewhere else, would require exotic matter with negative energy density, something that may not exist in sufficient quantities in the real universe. More recently, theoretical physicists working on quantum gravity and black hole thermodynamics have explored a deep connection between wormholes and quantum entanglement. The ER=EPR conjecture proposed by Moldesina and Susskind in 2013, which suggests that quantum entangled particles are connected by microscopic Einstein-Rosen bridges. Reality, at its deepest level, may be woven together not just by forces, but by these quantum geometric threads. Whether any of this is literally true, whether wormholes exist, whether they connect entangled particles, is still unknown. But the mathematics is rich, and the questions are among the deepest being asked in physics. Some physicists have speculated with varying degrees of seriousness that our universe itself may have originated inside a black hole in a higher dimensional parent universe. The idea is this: when a sufficiently massive star collapses to form a black hole, the singularity it creates might, in the right theoretical framework, seed the formation of a new region of space-time, expanding away from the parent universe into its own separate cosmos. The Big Bang that began our universe, in this picture, is the interior of a black hole viewed from within. The singularity at the center of a black hole corresponds to the singularity at the beginning of the Big Bang. Our expanding universe is, perhaps, the interior of a black hole that formed in some other universe. And the black holes in our universe are, perhaps, birthing new universes of their own. This is not a well-developed scientific theory. It is more a speculative metaphor, or at best a very preliminary theoretical framework, but it has attracted genuine interest from serious physicists, including Lee Smolin, who proposed a version of it he called cosmological natural selection. The idea is radical and unverifiable by current means, but it is not incoherent. The universe does not forbid imagination that reaches beyond the edges of what is known, and on the edge of sleep, in the soft dark of a room. Such speculation is perhaps the most natural thing in the world. Micro-black holes are hypothetical objects, tiny black holes of subatomic mass that might, in principle, be created in high-energy particle collisions, such as those inside the Large Hadron Collider at CERN. In certain theoretical models, particularly those involving extraspatial dimensions, gravity might become significantly stronger at very small scales than general relativity predicts, and under those conditions, collisions of the highest energy particles might produce microscopic black holes. This prospect attracted sensational media attention in the years leading up to the LHC's activation in 2008, with some public concern that the collider might create a black hole that would swallow the Earth. The scientific community addressed these concerns thoroughly. A micro-black hole created in a particle collider would have a mass far below the Planck mass, the minimum mass for a black hole of any stability, and would evaporate through Hawking radiation in an inconceivably short time, far less than a fraction of a nanosecond, releasing energy equivalent to only a tiny fraction of the collision energy itself. There would be no mechanism for it to grow, no possibility of it persisting. Cosmic rays, high-energy particles from space, have been colliding with the Earth's atmosphere for billions of years at energies far exceeding those of the LHC, without adverse consequences. No micro-black holes have been detected in LHC data, which itself places constraints on certain theoretical models. The Earth remains intact. The concerns were understandable. but the science was reassuring, and the LHC has gone on to produce extraordinary physics, including the discovery of the Higgs boson. The LIGO and Virgo detectors have, among their many gravitational wave detections, found some black hole mergers that are puzzling from the perspective of stellar evolution. In standard models of how massive stars die and collapse, there is a mass gap, a range of masses between about 50 and 130 solar masses where black holes should not be able to form directly from stellar collapse. This is because stars in this mass range undergo a process called pair instability pulsation or pair instability supernovae, which disrupts the star before a black hole can form, or creates a supernova that destroys the star entirely without leaving a remnant. Yet some gravitational wave detections have found black holes in exactly this forbidden mass range. One particularly notable event, GW 190521, involved the merger of black holes of about 66 and 85 solar masses, both squarely within the pair instability gap. These black holes are too massive to have formed directly from stellar collapse by conventional mechanisms. They may have been formed by previous mergers. Second-generation black holes, formed when earlier, smaller black holes merged. This implies the existence of dense environments, globular clusters, nuclear star clusters, or AGN accretion disks, where black holes can form, merge, and merge again, building up their mass generation by generation. Each generation larger than the last, the universe builds its most massive black holes, not just by feeding them gas, but by feeding them each other. A patient, ancient, beautiful cannibalism of the darkness. And finally, here at the end of our long, slow journey through the darkness, we arrive at perhaps the most important thing of all, black holes. For all their mystery and for all the things we do not yet understand about them, are among the most important and illuminating objects in the universe, not because they are dangerous or frightening or extreme, though they are all of those things, but because they are honest. They are the places where the universe refuses to let our theories remain comfortable. They are the places where general relativity and quantum mechanics are forced into the same room and made to confront their incompatibility. They are the places where the laws of physics break down and demand to be extended. Every great leap in our understanding of the universe, from Newton's gravity to Einstein's relativity, from classical mechanics to quantum theory, has been driven by confronting places where the old understanding failed. Black holes are the next such place. The information paradox, the nature of the singularity, the quantum geometry of the event horizon. These are the puzzles that will drive the next great revolution in physics. And that revolution, when it comes, will not just tell us about black holes. It will tell us about the nature of space, the nature of time, the nature of information, the nature of reality itself. The darkest objects in the universe, it turns out, are pointing us toward the brightest understanding. Rest now. The universe is still being figured out. You don't have to hold all of it tonight. Just let it rest with you, quietly, in the dark, and sleep. There you are, 100 quiet journeys into the darkness between the stars, each one ending here, with you, warm and still, at the threshold of sleep. The black holes are out there, patient and ancient and magnificent, bending time and swallowing light and keeping the deepest secrets of the universe. And you are here, safe, breathing slowly. The whole extraordinary cosmos running its slow, silent processes all around you. You don't need to understand it all tonight. You don't need to hold any of it. Just let it go. Let your thoughts drift like photons in the far dark. Let your breathing slow like time near the event horizon. Let the quiet take you. Sleep now. The universe will keep